We've been playing around with Simpson's rule lately, and what I want to do is compare Simpson's rule to some previous tools that we've learned in approximating definite integrals. And what we want to do is use these tools here, a left-Riemann sum, a trapezoidal sum, and use Simpson's rule to try to approximate this definite integral here, the definite integral from 0 to pi of sine of x. And I have sine of x graphed over here, and we're interested in using these approximation tools, and we're going to take 4 subintervals to do so. So why don't you pause the video and work on this? All right, assuming that you've given it a go, our first order of business is to figure out the length of our subintervals. So let's figure out what delta x is first. Delta x, again, not something new here. This is going to be the length of our interval, so pi minus 0 over our subintervals. So that's going to be 4 subintervals. So we have delta x, length of our subinterval, is going to be pi over 4. So graphing this out, this would look something like this. We'd have pi over 4 kind of right in here. And then we'd have pi over 2. That'd be somewhere right in there. Pi over 2. And then 3 pi over 4 would be somewhere kind of right in there. So this is 3 pi over 4. So these are our 4 subintervals, and again, we're just going to take a left Riemann sum first, and then we'll go through the other ones. So here we go, a left Riemann sum. A left Riemann sum here. And in order to do this, again, we're just going to be finding areas of rectangles. The base of our rectangles is going to be pi over 4, and then the height is going to be these left endpoints. So we're going to get the following. Delta x is pi over 4, base of our rectangles, and all of the heights that we're interested in are going to be these left endpoints. So we're going to have sine of 0, and then we're going to have sine of pi over 4, which is square root of 2 over 2. Sine of pi over 2 is just 1. And then sine of 3 pi over 4 is also square root of 2 over 2. And then simplifying this, we're going to get what? We're going to get pi over 4, and then in these parentheses here, we're going to get 1 plus the square root of 2, it looks like. So let's figure out what this is on a calculator. This is going to be approximately what? Let's see here. Let's grab our calculator, and let's go pi over 4, and then we're going to multiply this by 1 plus the square root of 2. 1 plus the square root of 2. What do we get? We get 1.896. Let's round it to that. So 1.896. This is what the left Riemann sum gives us. 1.896. So 1 down. Now let's move on and talk about a trapezoidal sum. And real quick, actually, I did graph these beforehand, so if you wanted to see visually what a left Riemann sum was doing, that's right over here. But let's move on. Let's keep going. Let's take a trapezoidal sum now. Let's look at a trapezoidal sum. Trapezoidal sum. Okay. And here, again, we're going to be taking delta x, and then we're going to be dividing it by 2. We're going to be making a bunch of trapezoids here. So we have delta x, pi over 4, divided by 2, and then we're going to be grabbing all of these points here. So we're going to take a sine of 0, so our endpoints are not going to have a 2 associated with them. So sine of 0 is, again, just 0, and then we're going to have sine of pi over 4, and we're going to be taking 2 times that. So we have 2 times sine of pi over 4, which is square root of 2 over 2. And then we have plus 2 times the sine of pi over 2, which is just 1. And then plus 2 times the sine of 3 pi over 4, which again is square root of 2 over 2. And then our last endpoint here is when sine is at sine of pi, which is just 0. So this is our trapezoidal sum, and all we need to do is simplify. So let's see what we get. We're going to have pi over 8, okay? And then in these parentheses here, these 2's are going to cancel. These 2's are going to cancel. So we're going to have 2 plus the square root of 2. Let me see if that's right. No, this is going to be 2 times. This is 2 times the square root of 2. So that's what we have, and we can still factor out a 2. So this is equal to, when we factor out of 2, we're going to have pi over 4 now. Pi over 4, and then we have 1 plus the square root of 2. And this is exactly what we got with our left Riemann sum. So we already know that this is going to be approximately 1.896. And graphing this out, that looks like this here. All right, so we've got two of these down. We have a left Riemann sum and a trapezoidal sum. Now we're going to take Simpson's rule. Let's figure out what Simpson's rule brings to the table. So Simpson's rule finally. Simpson's rule. And we're told that Simpson's rule is going to be delta x over 3. So this is going to be pi over 4 over 3. And then we're going to be taking this. So it's going to be f of 0, so that's going to be sine of 0, which is 0, and then plus 4 times sine of pi over 4, which again is a square root of 2 over 2. And then we have plus 2 times sine of pi over 2, which is 1, and then plus 4 times sine of 3 pi over 4, which again is square root of 2 over 2. And then finally, we add on sine of pi, which is just 0. So that is Simpson's rule drawn out. And let's see what this comes out to. Let's see if we get a better approximation. So we're going to be left with pi over 12. And then in parentheses here, we're going to have, this is 2 square roots of 2 plus another 2 square roots of 2. So this comes out to pi over 12. And then let's see, we can factor out this is going to be 2. So we can factor out a 2. And then in here, let's see, we're going to have 2 square roots of 2 and then plus 1. Let's see if I factored that right. Yes. So this is what we have left. This is going to go to 6. So we're going to have pi over 6 times this in the parentheses. So what does this come out to? Let's pull up the calculator. Let's see here. Let's see what we get. So let's clear that. And we're now going to be having pi over 6. So pi over 6, and then multiplying by, let's see, we're going to have 1 plus, and then we're going to have 2 times the square root of 2. And then what does this come out to? 2.00, and if we round, that's going to be 2.005. Let's say that, 2.005. So this is roughly 2.005. So let's see now how this compares to what the actual, and let me throw up the graph of this real quick. Again, this is making parabolas. This is constructing quadratic functions and finding the areas underneath them. But really, we want to see how good of an approximation this is. So let's go up and actually evaluate this definite integral and see what we get. So taking the definite integral of this, let's see. The antiderivative of sine of x is negative cosine of x. And then we evaluate this at 0 and pi. This comes out to what? Cosine of pi is negative 1 times negative 1, so that is 1. And then we have minus, and then cosine of 0 is 1 times negative 1. That's minus negative 1. So we're going to have, this is 2. This is 2. So the exact answer here is 2. And looking at the approximations that we took with all of these different methods, you can see that Simpson's rule does a really nice job. Let me scroll down a little more. You can see that Simpson's rule does a really nice job. That is very accurate. So hopefully that can give you some more trust in Simpson's rule. And in the next video, we're going to derive. We're going to give you some intuition on how Simpson's rule came to be.